Bismillahirrahmanirrahim. So here is a problem. Find the CDF and PDF of W is equal to XY when random variables X and Y have joint PDF. So we are given the joint PDF of two random variables X and Y, and we are to derive the CDF and PDF of the derived random variable W, which is a function of two random variables, right? So let's begin with the solution. So first thing to note here is that whether we are not to find the CDF or not, whenever we are trying to solve this kind of problem, we first need to find out the CDF of the derived random variable W. Once we get the CDF, then it's easier to find the PDF by just differentiating the CDF of W, right? The CDF will then be given by, for example, FW of W is equal to the first order derivative of the CDF. So now for our given function, given derived random variable, which is W is equal to XY, we see that the range for X is from 0 to 1 and for Y also from 0 to 1. So when X is equal to 0, Y is equal to 0, so then we see that W is equal to 0. Similarly, when X is equal to 1, Y is equal to 1, we see that W is equal to 1. So what we can infer from here is that the range of the derived random variable W is also from 0 to 1. That is, W is greater than or equal to 0 and less than or equal to 1. And once we have concluded this, we can see that the CDF of the random variable, derived random variable W, will be 0 for the interval W less than 0, and it will be 1 for W greater than 1. And what would be here when W is greater than or equal to 0 and less than or equal to 1? This is our topic of interest then. So if we are given a function, derived function, for example, W is equal to g x of y, it's a W is a function of any general function of x and y, then the CDF of W is given by, this is by the definition of the CDF, and we know that for the two random variables we have to integrate the PDF of the joint PDF over the area, right, which is given by g x of y less than or equal to W. So this formula gives us the CDF of the derived random variable W. So we are already given this here, the PDF of joint PDF of the random variables X and W, and this here, this limit here will help us determine the limits of this double integral. So what we can do now is to rewrite this formula for our particular case. So in our case, FW of W is given by, now in our case, this function gx of y is xy, right? So W is equal to xy. So xy less than or equal to W, right? And the CDF in our case is 1 here, and dx dy. So we have the right side here all done. What we need to know is to determine the limits. To determine these limits, it's always better to plot this function, right? This is x-axis, this is y-axis, and we know that that x is greater than or equal to 0, less than or equal to 1. So this is 0 here, for example, this is 1 here, and this is y is equal to 1 here, right? So this is the area specified by this interval. Now how do we plot w is equal to xy? So it could be, you can take an arbitrary value for w. For example, take xy is equal to 1 over 2. So then y is equal to 1 over 2x. You can put arbitrary values in this formula, and then you can draw the curve for w. So in our case, it will come out like this. All right. So this is the curve w is equal to xy. So this area xy less than or equal to w. So xy less than or equal to w is defined by this area here. All this area here below this curve gives us w is equal to w less than or equal to xy. Right. So we are interested to find this area which is bounded by this curve here on right side, w is equal to xy, then x-axis and y-axis, then this line here, and then this line here, right? So this is the area we are interested to find here. So you can see that we can divide this area into 3 regions. For example, if you draw this line here from this point and like this, and another line here from this here. So we have 3 areas. For example, we can label it A1, this area, this rectangle A1, and this rectangle here, this one A2, and this area here as A3, right? So rectangular area is easy to find. For example, this width and this length multiplied by this length will give us the area of this rectangle A1 here. This length and this height here will give us the area A2. For area A3, we will need to actually use integrals, double integrals, to find this area, which is bounded by this curve and then this line and this line here. So to find A1, we need to determine its width and height, and for this it is better that we first determine the values of this point here. You see this, that y is 1 here, right? So when y is 1 here, then w is, or x is equal to w. So this value here, x is equal to w. So x is equal to w here at this point. And at this point, again, we have x is equal to 1 here at this point, right? So when x is equal to 1, then y is equal to w here. So at this point, y is w. So this will help us determine the areas of these 2 rectangles. So for example, rectangle 1, we have A1 is equal to this width is given by w minus 0, right? So w minus 0 and multiplied by, this is 1 and this is 0, 1 minus 0. So the area of rectangle 1, the area A1, is w basically. And to calculate area A2, let's see. So this width here from this point to this point is 1 minus w along the x-axis, and along the y-axis we have w minus 0, right? So area A2 is given by w minus w squared. So this gives us the area A2. This gives us the area A1. We are left with to find area A3. So area A3 can be determined using the double integral. So A3 is given by, this is 1 here, dx and dy. Actually, this area can be found in 2 ways, depending upon the order of the integration that we use. So let us start with this order of integration. So in this case, we suppose a little strip here, right? And then we expand this strip up and down, to find the total area, this bounded area here, right? This area we are interested in of this region. So this is the limit for x, this will be the limit for y. How do we determine these limits? You see that this strip, it begins at x is equal to w, right? X is equal to w, and it goes on to this curve here. So this curve changes when the strip goes up and down. This curve changes. How does it change? This is determined by w is equal to xy. So at any particular point, this the value of x is given by w over y. So these are the limits for the x with respect to x, and for limits with respect to y, you see that we have to move this strip from this place to this place. So when we begin here, so we see that y is w here, and at this point y is 1 here. So these are the limits for this region. So let's now start doing the calculations. First we evaluate the internal integral. So integral with respect to x is evaluated here is x, and x is w to w over y, and we are still left with integration of dy, right? So a3 is equal to y is equal to w to 1, and then this is w over y minus w, and this is still to be integrated with respect to dy. So let's move further. Now we integrate with respect to y. So a3 is given by when you integrate dy over y, it results in the natural log of y. So w natural log of y minus wy, right? And this has limits from w to 1. So put in the limits, then we get this is w natural log of 1 minus w minus, then we put in w here, w natural log of w minus w squared, right? So a3 comes out to be, so natural log of 1 is 0, right? 0 minus w minus w log of w plus w square. So a3 is equal to minus w natural log of w plus w square. So this is the area a3 that we have calculated. As I told you earlier, we could have calculated area in a different way. For example, let's demonstrate that also. We could have taken the integral in a different order. So we could have taken y first and x later on. So dy by dx. So in this case, we assume a vertical strip here, right? So vertical strip here, y, in the y direction, it moves from y is equal to w and to this curve. When we move it from here, this little strip from here to here, so this upper side is bounded by this curve, and in this case y is equal to w over x, right? And we move this strip from here to here, which means from w to 1, x is equal to w to 1, right? So we first integrate with respect to y now. So we get y here, and y is equal to w over x, and we are still left with this integral dx. So a3 is then given by x is equal to w to 1. So this is w over x minus w and dx, right? And when we integrate it further, we again get, so this is w natural log of x minus wx, right? And the limits here are from w to 1. So A3 is now given by we substitute the limits here, w natural log of 1 minus w natural log of w minus w squared, right? So A3 is equal to natural log of 1 is 0, so this is 0 minus w natural log of w minus w squared, right? So A3 comes out to be minus w, sorry, this was plus here, minus w minus w natural log of w plus w squared. So it is the same result that we have obtained here, right? So this is how we obtained all these three areas. We can now add these three areas to find find fw of w within this region, right? So we have A1 is given by our result here, which is w, right? We have A2, which is given by this result here, w minus w square. We have A3, which is given by this result here that we obtained earlier, minus w, this result here, minus w minus w natural log of w plus w square. So we have all these three values. We need to add them together. So A is equal to area that we are interested in is given by A1 plus A2 plus A3. So A is equal to w plus w minus w square minus w natural log of w plus w squared. So right, so this w squared and this w squared cancel out, and this w and this minus w cancel out, and we are left with w and minus w natural log of w. So basically fw of w is equal to w minus w natural log of w for w greater than or equal to 0 and less than or equal to 1, right? So this is the result that we have achieved so far, and you must note that we could have calculated this area in a different way also. We could have calculated this CDF in a different way also. For example, if you would remember, CDF by definition is given by probability that w is less than or equal to w. Now we know that probability that w is less than or equal to w plus probability that w is greater than w is equal to 1, right? So what does it mean is, it means that probability that w less than or equal to w is equal to 1 minus probability that w is greater than w, right? So our CDF is also given by this formula, 1 minus probability that w is greater than w. So within this diagram that we have drawn earlier, it is this region, w greater than w is this region, right? So we can integrate and find this area and then subtract it from 1 to find CDF, right? So let's do that. So again, this can be done in two ways. We can assume a strip in the horizontal direction like this and then integrate first with respect to x and then with respect to y, or we can take a strip along the vertical axis and first integrate along the y axis, then along the x direction, right? So let us actually calculate using this way also. So fw of w is equal to 1 minus, so this is the area we are interested in. So in this case xy is greater than w here, so this is 1 dx and dy, right? So fw of w is equal to 1 minus, and now we are to find the limits for x and y here. So this is dx and this is dy here. So to find the limits, we again refer to this diagram. You see, we need to integrate using this horizontal strip, because we are integrating first with respect to x, then with respect to y. So x moves from this place to this place, so right? The length of this is the length of the strip. So what is the length of the strip here? On one direction it is bounded by this curve, and on one side this is bounded by this line. This line is easy. This is described by x is equal to 1, right? But this line is bounded by this curve, and at this curve x is equal to w over y, right? So x is equal to w over y to 1. So this is the limit for x. For the limit of y, we again refer to this diagram, and once we have used this strip, so we need to move this strip from this point to this point, right? So y is w here and y is 1 here. So the limits of y are w to 1, right? So now we can integrate first with respect to x and then with respect to y, right? So y is equal to w here, and this is 1, right? And we get x here, and x is w over y and till 1, and this is 1 minus y is equal to w to 1, and this is 1 minus w over, sorry, I left dy here. So 1 minus w over y and dy, right? So fw of w is 1 minus, now we integrate with respect to y. So this is y minus w natural log of y, and the limits are w to 1 now. So fw of w is 1 minus 1 minus w natural log of 1 minus w minus w natural log of w, right? Minus 1 minus w natural log of 1, then minus w and then minus w natural log of w, right? So this will be fw of w is 1 minus this is 1 minus 0, this is 0, minus w plus w natural log of w, right? So fw of w is given by 1 minus 1 plus w and minus w natural log of w. So fw w is w minus w natural log of w for w is greater than 0, less than or equal to 1. So okay, so we have determined w in a different way also. Again, we could have assumed this strip in this vertical direction and integrated along this line to find fw of w in a different way, but I leave it to you to do that. For now, we can summarize our results here. So fw of w is given by, this is 0 for w less than 0, this is w minus w natural log of w for w greater than or equal to 0, less than or equal to 1, and this is 1 for w greater than 1. So this is our results, and this is what we wanted, right, for the CDF. Now we need to find the PDF from here. So as I have already told you, the PDF is given by the log, the first differential, sorry, of the CDF. All right, so if we differentiate this, this is already a constant, this comes out to be 0. If we differentiate this, this is already a constant, this comes out to be 0. We are left with only this thing, right? And we can differentiate it to arrive at our answer, right? So d by dw w minus w natural log of w, right? So you know that the dw of w is 1, right? Minus we can integrate it, w multiplied by log of w. For example, we write here d dw dot w, and then plus we are left with log of w only, right? So this is 1 and minus w into 1 over w plus, sorry, this is minus natural log of w, right? So this is 1 minus log of w, right? So we're left with minus natural log of w. So the PDF is given by minus natural log of w for w is greater than 0 and less than 1, and this is 0 otherwise. So this is the result for the PDF.